Hey guys, what's the crack? How are you doing today? How are you doing this morning? Hey Evie, hey Regine, hey Sierra. Thank you for being so quick. What you guys been doing for the last 2 days then? The countdown's on for results, isn't it? What day is today? Today's Thursday, isn't it? So exactly 7 days to results. What do you all think? I'm guessing to do A-level physics at your current schools, you probably have to get what, like grade 7s in combined science? Is that right? Can you hear me okay? Give me like maybe a yes if you hear me fine. Hi Chloe. Ah, thank you Chloe. Thank you Evie. Yeah, I was worried there. I was like, oh dear, am I sitting here chatting to myself for like 10 minutes? I had a bit of panic because I didn't know what to do. Ari, you're not late, you're grand early. We're not starting for another minute. Sierra was just here a while ago, and I was just trying to make sure that I didn't make any mistakes setting up. So that's why I had the high in from a while ago. There's an echo. Maybe I just need to go a bit closer to you. Hopefully that's all right. So, you guys already know who I am, right? So hopefully you're all here from Tuesday. So Tuesday we spent quite a lot of time doing like thermal physics and everything. Hi Savanic, hi Katerina. And then today we're just gonna like keep going on with that a bit more and then go into the gas laws. And we talked about how, and if you weren't here on Tuesday and this is your first, is any of you here for the first time or are you all the same people? But if you're here for the first time, just again, remember, I loved astrophysics. And that's why I went into it. And then I just from there went on teaching. So I taught 3 different schools in London. And I'm looking forward to your results. Oh, I told lie. You say the results. Not is it the 22nd, isn't it? I think it's the 22nd anyway. Ah, you were here at the Crown courses. Ah, area, stop. You're going on my big head. Hi, Angel. So we're gonna just get started in a second, but I just want to say I checked the homework. It's actually good. Those of you did it. Well, I saw 47 of you did it, and it's not like everyone passed. So let me know what you think of the homework. Easy, hard. Well, it must have been easy if you all passed it, right? And good on you for getting it done. So again, like this summer school is kind of set up right, so you can see what the courses will be like through the year. So how it will be is we have a lesson, and then you'll have the homeworks after. Rajan, easy, awesome. Easy, Aaron, yeah, brilliant. Yeah, so it'll be like you do lesson, then you have the homeworks. Did anyone watch the homework solutions, or did you not bother, or did you not need it? Maybe if they were easy. But hopefully you find those quite helpful. So like you can kind of see like how it would be through the year. So you'll have a homework, and then say it got marked, you got one wrong, which none of you did. So awesome. You can then go to those homework solution videos, and it's just like me talking through exactly how I would have done it if it was my question. So hopefully you find those helpful. But let me know if there's anything you think could have been a bit better, because that's helpful for me too, right? But we'll see how we did then for the last day. So what do you remember? So last day we did like, what was I talking about? Gas laws. Last day we did a bit of units. So just have a go at these, sure.
Sorry, the mic needs to be closer. Also, could I change the camera settings? You can continue, sorry.
Yeah, scalars and vectors. Yeah, fine. Lovely. So which one is velocity? So nice, Angel. So Angel's talking about scalars and vectors. So what one is velocity? Yeah, velocity is vector. Lovely. Nice. Speed in a given directions here. That's nice. Do you remember the word beginning with M? We say it's got some beginning with M and direction. So see, you're just, instead of saying speed in a given direction, you say it's got a direction and a direction and a, what are we going to M? Magnitude, Chloe. Yes, thank you. That's what I wanted. Direction and magnitude. Yeah, I mentioned gas laws earlier. What was I talking about? Sorry, that was year 13. Yeah, of course, we did the baseline test. That was right. Yeah, lovely. Velocity is a vector. Nice. So yeah, 100%. So really nice everyone figured out velocity clearly is our vector from last day. And we said that they have both a magnitude, which is just us saying a number. So a magnitude and a direction, right? So then next one then is acceleration. So what do you think about acceleration? So how would you define acceleration? You define it maybe by an equation. Yeah, Rajan, that's exactly what I wanted. Rate of change of velocity. Yeah, perfect. So acceleration is the change in velocity over time. So remember last day on Tuesday, we saw that U, V, X, Y, Z. U comes before V in the alphabet. So U is always the initial speed. And that will come up a bit more when we start to do SUVATs. CFK, no worries. I'm glad you're here. Yeah, thank you, Angel. Brilliant. And then B, that was my phone. My dog. I got a German Shepherd. And he's got like a little girlfriend right now and another German Shepherd where we live. So they're trying to organize a play date. It's on silent now, maybe. But we said U was the initial speed. We said V then is going to be our final speed. So that's more important when we get to our SUVAT equations. So how we say this in word then is exactly what Rajan said a minute ago. When anything's over time, we say rate. So we say rate of change of velocity. So it's perfect. Okay, next one. I want to know what's wrong with that sentence. So it says the Earth, well, other than me not being able to use capital letters, the Earth orbits the sun at a constant velocity of 30 kilometers per second. What is wrong with the sentence? Can you explain your answer? Yeah, Fernandez, that's awesome too. Yeah, brilliant. Thank you, Area. Yeah, straight on it, right? We can't say constant velocity, right? Because it's not a constant velocity. Yeah, Rajan, that's exactly what I wanted. Yes, brilliant, because velocities do a direction. Nice. Okay, so that person's got confused there with their scalars and their vectors, right? So it's not velocity. We want to say that it's a constant speed of 30 kilometers per second. And we can't say it's a constant velocity because if we look at it again, remember, right here, it's velocity in that direction, that orange arrow. But if the Earth, when it gets to here, the velocity again is always, remember, at the tangent to our curve. So we can clearly see, even though the number's the same, it's always going at 30 kilometers per second. So it's still always moving at 30 kilometers per second. It's just going at different directions each time. So because the direction is constantly changing, we can't say that it's a constant velocity, right? Yeah. Yeah, beautiful. Brilliant answers. Yeah, and nice you're praising each other. Yeah, great. Okay, what about this one? So we started this last day as well. So I said, I've got an airplane and it's going at 900 kilometers per hour. So what that means is in 1 hour, it can travel 900 kilometers. So how can I figure out how many meters it goes in 1 second? Give it a go there, sure, and pop it in the chat. So if it goes 900 kilometers in 1 hour, how many meters would it go in a second? And then just remember as last time, normally in GCSEs, you saw it as meters per second. But remember your A-levels now, we can't write it like that anymore. So write in indices. So remember we said last day in math, 1 over x is x to the minus 1. So a meter over a second, that's how it becomes meters to seconds to the minus 1. So pop in the chat when you think you can figure it out. So 900 kilometers, they can go in 1 hour. How many meters do you think they can go in 1 second? So the first thing I'd probably figure out is how many meters they can travel in 1 hour. Yeah, so 900 kilometers is what they can go 1 hour. So how many meters can go 1 hour? It's going to be 900,000 or 900 times 10 to the power of 3. Yeah, Gabriel, straight on it. Yeah, perfect. Good job. So that's how many meters they can go in 1 hour. So if they can go this many meters in a whole hour, clearly if I only have 1 second, it's going to be much less. So that's how I know to divide. So I have to divide by 60 to put it into minutes, and then divide by 60 again to put it into seconds. So that's why we do this number, divide it by 60 twice. So divide by 60 twice, or divide by 3,600, which Angel said. And then that's why we get our final number there of 250 meters per second. Yeah, beautiful. And Rishit, thank you for putting the units into your equation. Yeah, so you can't just divide by 3,600 because if you did that, your final answer would be in kilometers per second. So that's why you can't just divide by 3,600. You still have to multiply by 1,000 first and then divide by your 3,600. Yeah. Yeah. Awesome. Okay, so our final answer there is 250 meters per second. Okay, what about this one? Speed of sound in air, and this is a true fact. So sound can travel 330 meters in 1 second in air. How many kilometers could sound go in 1 hour? Okay, so give it a go and then pop in the chat. So if sound can travel 330 meters in a second, how many kilometers could it go in 1 hour? See if you can figure it out. And then pop in the chat. Multiply by 3,600 to put it into hours, and then divide by 1,800. Why divide by 1,800? Area. At CFK, it's not allowed anymore. So for example, when we're writing tables in A-level physics, so say I'm writing forces are measured in slash newtons, right? So in telling them that's how we're going to write, that's what that symbol's only for now when you're writing your tables. So because physics is more math, so I think physics and GCSE you can kind of quite separate from math quite a bit, especially because you might have been taught equation triangles. But math in physics is the exact same as math now in your actual math classes, right? So you'd never write a unit. You'd never write 1 over x, would you? You can't write that. You'd always write in math x to the power of -1. So we just have to write it the way you would do in math now. So it has to be in indice form. Okay, so Demiliad, sorry if I said that wrong. Demiliad says it's exact same that I got. Yeah, good on you. So limit say it's going to be 1188 kilometers per hour. Yeah, perfect. So the way I'd think about it, if it can go 330 meters in 1 second, I want to know how many kilometers that is in 1 second. So first thing is I'm just converting meters into kilometers. So meters into kilometers, I just divide by 1,000. So that's 0.33 kilometers in 1 second. So that's how many kilometers can go in 1 second. If I have to go in 1 hour, that's much longer time. So that's why I can multiply by 60 twice, right? Multiply by 60 once to put it into minutes, and then multiply by 60 again to put it into my hours. So because I did that to this side, I have to do it to this side twice. So we're going to multiply by 60 twice, or multiply by 3,600, and you get a final answer of 1188 kilometers per hour. Okay, so just always do it in like steps. Just try and imagine how many meters it can go in 1 second. If it was 1 hour, clearly it can go much further. Yeah. Monkey pickle pants, straight on it too. Good job. User 96, lovely. And I know it's a bit annoying to put it into the chat, but just be careful. So kilometers per hour, if you want to pop it into the chat, you just have to hit Shift and 6 on your keyboard, and that'll give you that little arrow, and then just write -1. It's kind of how you write it if you're popping it in the chat. Area. Yeah, grand. I wondered where you got 1,800 from there. Yeah, good job. Okay, so what we're doing today clearly is DT graphs. Okay, so DT is we're doing distance time graphs, and then we're also going to look at the difference between a distance time graph and a displacement time graph. Okay, so let's say I'm at schools and then I want to go from school towards the shops, right? Nice thing about physics is we don't have to bother writing all this information. Okay, so that's why my spelling got significantly worse over the years, because you barely spell anything in physics, right? You don't even write F. When you're writing force, you just write F. When you're writing proportional, you just write a symbol. You don't have to write proportional. When you're writing multiply, divide, it's a slash. Do you know what I mean? Like you barely ever spell any words. Acceleration is just A. So again, what we're saying here is the nice thing about the graphs is instead of writing all this information out, we just always pop it onto the graphs. Okay? So first thing about graphs is that you have to look at your axes. They always try to get you this in your year 12 and year 13 exams, okay? So just make sure the first thing is you look at your axes and you want to see what units they've written it in. So maybe it's kilometers, maybe it's meters, okay? So always check there first, and then go to your x-axis and see what unit have they given you time in. Maybe they didn't give it to you seconds. Sometimes they might give it to you minutes or hours. So always just check that. And then another thing they like to do in your A-levels is they're not always will start your graphs at 0, 0. So just always check here first to see where did they actually start the graph. Because sometimes they might start the y-axis of number 10 instead of the number 0. Okay, so just that's things just to always be aware of because they do that quite often. And then those 1 marks actually make quite a big difference because last year's paper, you basically only had to get 56% to get an A. I think you had to get 60% to get an A star, right? So those 1 marks are actually quite different. Yeah, area, right? Like they always try to catch out with those little things. So you just want to always watch for it. Okay, so again, so here's my sentence here. It says, I leave school on foot and begin walking towards the shops, covering the first 6 meters, 12 seconds, right? So instead of saying all that there, all I need to do is find the number 12, find the number 6, and I draw my straight line. Easy, right? Yeah. Well, at least like, you know, to check now, you're like, and you did it. So this one then, if I stopped to chat, so my distance, if I stopped, I never moved any distance, which is why it's a flat line. And then if I decided to run the remainder, I just have to say that I went another the remaining 24 meters to shop in 10 seconds. So then I ran the last 24 meters in 10 seconds. So I see if I started at 20, another 10 seconds takes me 30. And if I was at 5 meters already and I had to go another 24, that's why we end up here up at 29. Okay. So that's we can just quickly see it. And the nice thing about graphs, you can get all the information quickly, right? So right here, I can see the line is flat. So that means I was stopped. I know that straight away. That's what it means in a distance time graph. And then just by looking at it, I know I must have been faster here because again, the gradient is more steep. So that's stuff you've done from GCSEs, right? So this is just a quick recap before we go into the new A-level stuff. Okay, so again, just what we just said. So we know if a steeper line, so a line that's more steep, it's got a greater gradient, that's when we're going faster. And if the line is flat, that's how we know we're stopped. Rishit, yeah, that's raging. But that's the type of stuff we're going to go over, right? About whether what deceleration is different from acceleration, positive and negative numbers, right? Okay, so really quickly then, can you try number 1? So just easy for me in the chat. So if you printed the workbook, awesome. You just match them up in your workbook. Or if you want to pop in the chat so I can see how you're doing, just match up 1, 2, and 3 to A, B, or C. So for example, graph 1, is it going to match description A, description B, or description C? So these are all my distance time graphs. So these are all distance time graphs. So again, so just looking at the graph, looking at the 3 descriptions and then thinking what's going to match to which, and then pop it in the chat so I can see how we're doing as well. One to C, Chloe says. Thank you for being first, Chloe. So Chloe says 1 is going to go C. Yeah, I would agree. Good job. So it says, I run to the shop from home. When I reach the stop, I immediately turn around and walk home, right? That is right. Like, so they're going a further distance. They've turned around and went home. 1 to C probably makes sense. 3 is going to B. Yeah, nice. What I would look at is here where it says stops. So we know stop is always going to be that flat line there. So that's why it has to be 3 to B. Nice. Monkey pickle pants. Do you guys pick these names so that it's weird for people to say them out loud? Is that what it is? Regine, yeah, beautiful. 2 to A then, good job. Because what it says is it drives across the top of the mountain at a faster speed. So we knew this part of the line must have a steeper gradient than the first part of the line. Okay. So the second question then was, are these actually distance time graphs? So distance time graphs is what you drew it all for GCSEs, but are these actually distance time graphs? So look at this one, for example. It said the person ran to the shop from home. So we've got our distances increase. We're going big distances. And then it says they turned around and went home. Yeah, thank you, Eric. Right, clearly it's not a distance time graph. Do you remember the word for what it is instead? It's not a distance time graph. It must be a... What do you call it instead? Because if it was a distance time graph, the distance they travel would just keep increasing, right? Because they went at a faster speed, just be a steeper line there. Their distance would just keep increasing over time. But what they've done here, if they try to show you that they've went back to where they started. Yeah, thank you, Monkey Pick Pants. Good job. So it's going to be displacement here because the direction matters. So displacement, remember, a nice way to think about it is it's how far did you finish from where you started? So if we started at 0 here, I can clearly see I went away from 0, away from 0. I got really far away and then I turned around and went back towards where I started. So we look here at graph 1, our final displacement, so where we ended from where we started, was actually 0 meters. right? Because they've ended up exactly back where they started. So that's a displacement time graph. So that's just one of the big changes again about year 12 and year 13. You won't get distance time graphs. You'll get displacement time graphs, because what you have to think about is how the direction has changed each time. Okay. Yeah, nice. Oops, sorry. Okay, so next one then is just, we're going to look over these displacement time graphs and we're just going to comment what they say. Okay, so in the chat, can you just pop down, what do you think each one of these is saying? What information are we getting from our distance time graphs? Area. How proactive of you. That's brilliant. And Area, that's awesome, because you can't slack in year 12 at all. So I know, like GCSE, a lot of you might have started in year 9, and you've got year 9 to do GCSEs, you've got year 10 to do GCSEs, and you don't do exam to year 11. But hopefully you've all learned from your GCSEs, you can't leave it to the last few months, right? And there's nothing that rings truer than that than in your year 12s. Because I don't know why, but every year kids don't get it that your predicted grades are done at the end of year 12, right? So say you can't be like year 12, oh, I'll get C's all year, C's, and then you're going to go to year 13 and try to get A's, because your predicted grade that will go to UCAS is done at the end of year 12, right? So you just need to make sure that you hit year 12 getting A's all year, and then your predicted grade will be an A. So then when you're in year 13, you can just make sure you actually end up attaining that, right? So just for Area said there, because she's trying to be on these lessons, right? Just make sure when you go into year 12, you recognize that your predicted grade is the end of that year, right? You don't want to mess yourself up just because you had a bit of a good time in your first year 12 class, right? Okay, so sorry, Monkey Pick a Pants says not moving. Yeah, but can we get like maybe a better way of saying not moving? Because you're not really going to write not moving. Well, one, not moving is 2 words. So like, how can we save time and like simplify it a little bit, I guess? Demilia says constant velocity. Yes. Can you give me a word between constant velocity? So I'm trying to increase yours, I guess. Constant decreasing velocity. Yeah, nice. Demilia. So can you do the same thing you did there for 3 for number 2? Nice. So constant decreasing is nice. Decreasing velocity. Yes. Thank you, Risha. Thank you, Brian. Yeah, good job. This one is stationary. Nice. Stationary means it's not moving or stopped. Yeah. CFK, nice. Stationary. Area, enjoy yourself. Well, yeah, that's what life's for, right? Stationary, nice. Monkey Pick a Pants, yeah, nice fix. Stationary. So can we do what Demilia did for number 3 for number 2? So she said it was a constant velocity, but there's a word missing. Constant increase in velocity, yep, or constant positive, thank you for fixing it, constant positive velocity. So, and then this one, instead of writing decreasing, it's probably better to write constant negative velocity. Yep, nice. Displacement over time. Couldn't one be moving around a point in a circle? So if something was going in a circle, it's accelerating. So it wouldn't be stopped. Do you see? So this is telling us that something's stationary or stopped. We're going to go over things moving in circles as well. What are we saying for, we're saying for number 4, it's accelerating. Yes, good job. So number 4 is accelerating, nice. So the way we can do that is, again, nice everyone remembered, in a displacement time graph, the gradient of the line gives you the velocity. So it's nice you remembered that. So remember, the gradient is just going to be whatever my vertical is divided by my horizontal. So the vertical divided by the horizontal here gives me a positive number. Whereas here, the vertical divided by the horizontal give me a negative number. So when we look here, we know the gradient gives us the velocity. Okay, so we can clearly see here, the gradient's quite low here, but here the gradient's quite steep. So if the gradient is getting bigger, that must mean the velocity is getting greater, which is how we know that one's accelerating. It's really nice. And then the last one, yeah, Monkey Pink Pants, perfect, is decelerating. Nice. So this one is decelerating. Again, because we know the gradient gives us velocity, sorry. So if I look here, if I take a tangent here, we're going to look at what tangent is in a second, but you probably know it from your math classes. If I look here, that gradient is really steep. But if I look here, the gradient's basically flat. So because of that, I can't spell flat. So because of that, we can see the gradient's getting less steep over time. So the velocity isn't as, the velocity here is really high, but the velocity here is really low. So it must have been decelerating. Yeah, nice. So these things are really important because when you have to start analyzing your graphs, you have to make sure you're okay that this line's getting steeper, so it's accelerating, and this time it's getting less steep, so it's decelerating. So these don't come up as much in GCSEs, but they come up quite a lot in your A levels. Okay, so now we're just going to look at analyzing them. So I wrote distance here, but it could have been displacement. It doesn't matter. Either way, it's always going away from us. So can you quickly tell me what's happening at part A, B, and C on that first image? So what's happening at A, B, and C on that first image? As much detail as you can, right? Because they've given you numbers this time. So what's happening at A, B, and C on that first image? Graph is on a plateau. Yeah. CFK, yep. Yep, lovely. Constant positive velocity from 0 to 2 seconds, increasing constant positive velocity. Nice, but remember we've got numbers now, so you need to use them. So the last graphs, they didn't give us any numbers. So in the last graph, if it looked like this, that was fine just to say constant positive velocity because you couldn't actually give me any data. But I've given you data here now, so you just want to start putting in numbers. Yeah, Rajan, exactly what I want, right? So again, we know that the gradient of those lines, which we said over here, is the change in y divided by the change in x. So m is the letter in physics we always use to represent what the gradient is. So the gradient is the change in y over the change in x. So clearly I can see here, the change in y, it increased to 4. So it's going to be, well, I don't know why it was written around that way, but it increased to 4 divided by 2 gives me 2 meters per second. Nice. So constant positive velocity of 2 meters per second. Nice. Yep, good job. Then she's stationary. Thank you, Monkey Pig Pants. Stationary for 2 seconds. And then in C, what are we going to say? Angel says steeper constant velocity from 4 to 6 seconds. Yep, but again, we want some data. So what actually is that velocity? So we want to know what the change in y is divided by the change in x. So it starts at 4. And it ends at 10. So there's 4, there's 10. And like Angel says, it starts at 4 and 6. So how do we find the gradient of the line? Yeah, Fab, Rashid, Fab, Gabriel. Yeah, nice. So the change in y, the change in height here is my 6. And the change in x here is 2. So all I have to do is the change in y divided by my change in x. And I get 3 meters per second of a constant positive velocity. Yeah, nice. Brilliant. Okay, now down here, we're looking at displacement time graph. So again, what's happening at A, what's happening at B, and what's happening at C. What's happening at A, B, and C. So we look at A, again, I want to figure out what the gradient of that line is. So do you think it's getting faster? Do you think it's getting slower? What do you think it's doing? Negative constant velocity. Yeah, good job. So it's going to be a negative number. It is a constant velocity. So is it a velocity is it something that's getting faster? Is it something that's getting slower? What is the velocity? What is that velocity? Yeah, right. It's not getting faster or slower. Thank you. It's constant. Thank you. Constant negative velocity. Nice. Yeah, just declining. That's perfect. That's all I want to talk about. So it's just going, remember displacement. Remember we talked last day that positive numbers, we're always going to say something going towards the right. And negative numbers just mean anything going towards the left. So what we're saying here is this may be a car that's parked. And the first thing that it's doing is it's maybe reversing, right? It's going the opposite direction. It's going the backward direction in a constant velocity. Yeah, so nice. What we do is the change in y. So change is the final is -4. The initial was 0. So the change is the final minus the initial. So 0. So we do final minus initial. The final speed that it ended up at is -4. Its initial was 0. So that change is -4. And then the change in our x there is 2. So negative 4 divided by 2 gives me negative 2 meters per second. So perfect. Nice. And then, so we know the first thing the car is doing is moving backwards at 2 meters per second. And we're going to say backwards. So instead of drawing these arrows now, I can give my negative to represent backwards, 2 meters per second. And then it's stationary. Thank you, Monkey Pick Pants. It's stationary again for 2 seconds. And then C. What's she doing in C? So this displacement, so it was moving further and further away from us. So it's getting further and further away from us. Then it stopped for a little bit. And then here, what did it do? So again, we just saw the car is getting further and further away from us. So it's moving away from us. It's moved away by 4 meters. Then it stopped when it got 4 meters away. Yep, nice. And then it traveled at a constant positive velocity. Good job. Because here is negative 4. Here is 6. So that change in y there is final minus initial. 6 minus 4 gives me 10. So 10 over, and it started at 4, and at 6, 2. So 10 divided by 2. Oh, careful. I don't think. 10 meters per second. You sure? Unless my math's off here. I'm getting 5. Yeah, Angel. Yeah, thank you. Just making sure we got this in there. So 5 meters per second, right? Because again, if we look at it, just here, it starts at negative 4. It ends up at 6. So that change in height there, the change in y, we can do final minus initial to give us 10. So the change in height is 10. And the total time it took to do that was between 4, was when it was at negative 4, and 6 when it was 6. So that total time to do that was over the 2 seconds. So do change in y divided by change in x to give me 5 meters per second. So what happened then was our car clearly moved 4 meters away from us. It stopped this 4 meters away from us. And then here, it starts to come back to where it started. Okay, so we can clearly see that. So what it must have done is on a U-turn. Oops, sorry. It did a U-turn, came back to where it started, but then it didn't stop. It just kept going further away from us. So then it went another 6 meters away from where she started. So that's where our car has ended up. So again, just have a look at that graph to make sure we're okay with what's happened with that journey of that car again, okay? So again, here, we can clearly see that it moved 4 meters away from us. So the car went 4 meters away from us. It stopped for the 2 seconds, that's what we said. And then what it did is its displacement went back to where it started. So it must have turned around and went back to where it started, but it didn't stop. It just kept moving that next 6 meters to where it ended. So this, when it turned around, it just kept moving the whole time at 5 meters per second. Yeah, grand. Thank you, Arian. Okay, so we're going to move on, try some more now. Okay, so this one, I just want you to pop in the chat what's happening. So let me change my color because I think yellow was a rubbish color to pick, wasn't it? So what's happening at A, what's happening at B, what's happening at C, and what's happening at D? If you can pop in the chat. So again, remember, first thing you do is we're always going to check our axes. Displacements in meters, I like that. Time is in seconds, I like it. And it started at 0, 0, I like it. So it's quite a nice graph for us. No area, no worries. I had a bit of a nightmare yesterday in a GCSE lesson with internet. I get it, trust. So what do you think is happening? A, B, and C. So C of K says it's an increase in positive constant velocity of 2 meters per second. I agree it's increasing. I agree it's positive. And then 2, nice, good job. So for A, if we look at what CFK said, he said the change in velocity, so 0 to 8, so change in y there is 8 over a change in x was 4. So I do 8 over 4 to give me 2 meters per second. Nice. Yep, they're kind of all stationary. I didn't know it was there, but yeah, they're all stationary. So B, it's going to be stationary for the 2 seconds. Nice, increase comes plus, nice. C, we're thinking it's accelerating. So do we agree? Does everyone think that C is something that's accelerating? D is deaccelerating. So do we agree? What do you think? object accelerates and then decelerates. So we're all saying accelerates and then decelerates. So we look at this part C, it looks like what it's doing is it has like a bit of a bump and then it goes like this and then it goes like this. So at the very start, I do agree that it's accelerating, right? Because we can see that's quite steep. So right here, it's definitely accelerating. But then what about here, right there? And then how does that graph look different? Remember, the gradient is our acceleration. So yeah, so if we look here, does everyone see that here it's clearly accelerating? But again, look at that curve. The curve at part C goes like this. So it's actually getting less steep over time. So it initially accelerated, but then it started to deaccelerate. Right? So it's still the displacement, it's still getting further and further away from us. So it might be the car was stopped, they hit the accelerator, the accelerate is really high at the start, and then the person starts to take their foot off the throttle. So the car stops accelerating as much, right? So they're still going further away from us. The car's always getting further away. But here, the light might have went green, they hit the foot in the throttle, acceleration is really high, and then they start to take the foot off the throttle. So that's why they start to decelerate. Yeah. And at this point right here, we can see the displacement now starts to change direction. So at this point right here, they've turned around. They start to come back towards us. But again, if I look at the shape of the graph in part D, it's going like this. So again, if we look at the gradient, it's not really steep here, but it's really steep here. So if it's getting steeper over time, that's actually accelerating. Okay, it's just accelerating in a different direction. Okay, so just you have to be careful with those words, right? So acceleration means it's getting faster. It's just going in accelerating faster in a different direction. Okay, so give me like a positive if we're feeling happy there, and a negative if we're like, nope. Can you do that again, please? Okay, so I know this is a little bit of a mind change, but you just have to always, what you want to do is always look at the shape of the line and see what's actually happening. So we want to look and see this one's getting less steep over time, whereas this section D is getting more steep over time. Yep, CFK, thank you. Chloe, thank you. Yes, brilliant. Okay, so we'll move on then and try another one. So the next thing you have to do in physics, thank you, Rajan. The next thing you got to do in physics is tangents to lines. So if you did triple physics for GCSE, you probably did this quite a bit. And if you did combined, you definitely did this in your math classes, right? So what we want to say first is the average is the nice one, right? So they asked us this, yeah, area, brilliant, right? So the average is a nice one. If they ask you about average, then you're pretty happy because it's easy, because all you got to do is find what the total displacement is, where it ends up, over the total time, and you divide them, right? So that's a nice one. If they ask you about instantaneous, that means exactly at that point in time, I want to know what's happening. So let's say they asked me about the instantaneous velocity at 20 seconds. So the first time they said 20 seconds. So I find 20 seconds, I go up to my graph, I draw a point, and then I draw my tangent to my line, and I find the gradient, the change in y over the change in x of that tangent, okay? Or the one here, it might have said, what is the instantaneous velocity at 40 seconds? What we do is we plot a point at 40 seconds, and then you take your ruler and you draw a tangent to that line, okay? So you draw a tangent to the line, and then all you do is you find your change in y over your change in x. So for example, if I looked at this one, here I've marked that's 192, and here that's 52. So my change in y there is going to be 140, if my mental math is good, hopefully. And then the change in x here, I can see it's probably at 32, but it'll be a little easier to see that in your test, and 50. So that change there is going to be 18. So that's how I find out what the gradient of that line is. Okay. Key things here is, so I'm just going to rub this out and do it again. Key things here is, oh, area, my mental math is shocking. All my friends make fun of it that I'm a physics teacher and have bad mental math. But I swear, like you use, because I did astrophysics and I did math, chemistry, and physics and biology, right? You constantly have your calculator in front of you. So you're just constantly plugging things in. So you actually rarely have to use your head to do math because you're always just plugging things in. So yeah, my mental math is actually shocking compared to some people. People, the best mental math are people who work in shops. My sister's mental math is shocking. She works in Tesco's and she just can like quickly multiply numbers out because you're constantly dealing with money, right? But anyway, enough about shops. But sorry, the thing I wanted to highlight here, okay, and again, it seems it's such a small thing, but the amount of kids who lose marks for it in A levels is shocking. When you draw your triangles, you have to make sure they're always greater than 5 centimeters on one side. And they do check that in your test, okay? So I'm going to talk about that again in the next slide. But for example, what I mean by that is, so say you did your tangent here to this line and you decided, I'm going to find the gradient of that little section. Okay, so I'm just going to rub this all out so you can see what I mean. So let's say I drew my tangent to my line and I wanted to find the gradient of this little section. So I said that number there is probably 130 and that number there is probably something like 90 and that number there is probably 35 and that number there is probably 45. And I decided to find the gradient of this change in y over this change in x. You'll straight away lose marks. Okay, they don't like it if you do that. They have to make sure that when you draw your triangle on your page, one of the sides is bigger than 5 centimeters. That's like that's what they look for in your test. But I would just say, don't be taking out a ruler measuring the length of your line. Just always make your tangent as big as possible. Okay. So for example, that's a pretty good tangent there. That's not too bad. But if it was my test, I would make sure that line gets extended out as long as possible all across the graph. And then what you should do is you want to find the gradient of the biggest triangle you can. Okay. So what I do there is I'll say that number is 240 and that's my change in y. It starts at 0, it's 240 over this change in x, okay? And it's because of something that you learn when you do the practical part of physics. It's because of the uncertainty in your measurements, okay? So we'll talk about that another day. But for right now, just remember, you want to make sure your triangle is as big as possible, okay? Okay, so really quickly in chat then to see if we're good. You should have this printed in your book. And if you don't have it printed in your book, just maybe talk through what you would do, because I understand sometimes a bit, I never had a printer in my house. It's a bit annoying, right, to print sometimes. So maybe you have it on your iPad and you can just like sketch a line on your iPad. So for this one, first of all, just tell me what's the average velocity. That's the nice one. And then the second one is, what is the instantaneous velocity at 2 and at 7? Yeah, Area, if you don't have the workbook, again, it's sometimes nice to have it, right? Because for me, I have to write math all the time. I can't do it. I can't just think about math. I have to write and draw pictures. So that's why the workbooks are really good. And again, they're good, again, if you're like revising, you want to look back at what we did. But at the same time, they're always there. They're always going to be up. So you can always go back to them and print them another time and then retest yourself and things, which is always quite good. Okay, so pop in the chat, what is the average velocity here and what's the instantaneous velocity at 2 seconds and at 7 seconds? Area, I'm pretty sure you're on it. I don't think you have to watch it again. I'm sure you'll be able to remember it all and just fill the book in. Average is 10, beautiful, thank you. So remember, average is a nice one. All we got to do is the total displacement divided by the total time. So S stands for displacement, and I just remember it because it's the third letter, okay? D stands for distance, okay? So D is our distance, displacement is your S. So the total displacement is 100, and the total time it took that is 10 seconds. So exactly what Gabriel said there, and thank you, Area, for your units. It's 10 meters per second. Because again, we check our units first to make sure they actually give us meters per second, and we check our origin to make sure it actually started at 0, 0, okay? Before we do anything else. Okay, next one then is if I want instantaneous velocity at 2 seconds and 7 seconds. So I'll do 2 seconds first. I find my 2 seconds, plop a point. I find my 7 seconds, plop a point. And what they want me to do then, in order for me to calculate the velocity of those points, so instantaneous, so I just saw it there, instantaneous is exactly at that moment. Right? So at exactly 2 seconds, what speed, what velocity is that car going at, or the object or the train? So what we do is exactly that moment. The only way to find the gradient at exactly that one moment is I take my ruler and I want to draw a tangent to that line. Okay, remember you make the triangle as big as possible, really exaggerate it, because they lose you marks if you decided to do this tiny little triangle. Okay, which everyone does all the time. I don't know why. Make your triangle big, right? So for me, mine starts at 1 and mine's ends at 10. So my base there is going to be 9. And for me, it ends at 50 and it started at 0. So my height there is 50. So at 2 seconds, my velocity is going to be my change in y, which was 50, divided by my change in x, which was 9. So I do 50 divided by 9. And again, my mental math is shocking. So my calculator says it's 5.56 meters per second. And again, I didn't use a ruler, right? Obviously, you'd use a ruler, but I can't get a ruler out right now when I'm trying to do this on the computer. Someday I'll figure out how to. But yeah, so you just use a ruler to do it. Okay. So you'll probably get a slightly different number because you'll be using a ruler right now and you'll have a better tangent. So then the other one is, if I was looking at my 7 seconds, I go over here, I want to draw a tangent to my curve. So it's probably something along those lines there. And again, I want to extend that line out, but I'll be using a ruler as long as possible to find the gradient of that line. So for me, my line starts here, which is 20, 2, 4, 6, 8, 10, 20, 2, 4, 24, and it's ending at 100. So my height of that line is going to be 76. And then my base of that line is right here. And that number right there is going to be 8.2. And it started at 0. So for my one at 7 seconds, I do my change in y, which was 76, divided by my change in x, which was 8.2. Right? So we just do 76 divided by 8.2, and then we get our final answer for our meters per second. And again, big thing about this is big as triangles as possible, right? Fab. Okay. This one, I just want to talk about why we do it, okay? So again, I mentioned a minute ago that it's because of percentage uncertainty. Does anyone know what the uncertainty is in your ruler? So we're using rulers to measure these lines, right? What is the uncertainty or the resolution is another way to say it? What is the resolution of your ruler or the uncertainty in a ruler? What's the resolution or the uncertainty in a ruler? Yeah, Rishit, awesome, good job. Yeah, area is another way to say it. Good job. So, and I like that Rishit put his units in it. So it is plus or minus 1 millimeter or radian. Yeah, nice. Or you could say positive or minus 0.1 centimeters, right? So what that means is if I was to measure a length of line, so say my line is 5 centimeters long, what that means is 5 centimeters, let's put it into millimeters. So it's nice. So what that means is, say it's 50 millimeters. What that means is my ruler is going to be off by plus or minus 1 millimeter. So I might think it's 50, but really it could be 49 millimeters or it could be 51 millimeters. And it can be any number between those two because of the uncertainty in my ruler. Okay. Whereas if I was to measure something that's 100 centimeters in length, or say that's going to be 1,000 millimeters, either it's plus or minus 1 millimeter, either it's 999 millimeters long, or it's 1,001 millimeters long, and any number between those. So hopefully you can see there, if we look at the percentage here, that's like, if it's only 5 centimeters, it's only 50 millimeters in length, that's quite a big difference between my two numbers. But if it's 1,000 millimeters in length, that's because it's so big anyway, it's not really that much of a difference. So what we're trying to say is if you measure lines with your rulers, because of your uncertainty in your ruler, that's a big percentage error there. Whereas if I was to measure the biggest triangles possible, that error doesn't matter as much as my final result. Okay, so that's why they're checking to see if you understand that. And it's the same with this, right? If I want to measure the thickness of a single piece of paper, I'm not going to get my ruler out and try to measure what that length is there, because clearly it's probably around 1 millimeter. So the uncertainty is a big percentage of it. So what I should do is probably get like a block of like 100 sheets of paper, measure the length of those 100 sheets, and then divide by 100 to get 1. Okay, so you'll start doing more of this stuff when you do practical physics. Okay, so again, key thing today, look at your axes, look where it starts, large triangles, right? Okay, we're doing 2 more slides then, I think. And then that's us done today. So you've been flying through. So we've got about 10 minutes left. So I just want to see if you can draw it yourselves in your booklets. And then once you're pretty happy about it, see if you can maybe describe what you drew in the chat. So it says, Einstein throws a ball vertical upwards. So for me, again, I need pictures all the time. I don't like all the words. So I would imagine a person, and it says they throw a ball vertically upwards. It says he catches it when it comes back down. So a ball's going up and it comes back down. sketch and annotate a displacement time graph. So sketching it means you did have, area displacement time graph. So time, I'm going to say is measured in seconds. My displacement is going to be measured in meters. And then how would we sketch it? Oh, it's not a triangle. Yeah, and I think like area, just because you said that they were talking about Einstein, I think that when you're in high school, I know you get imposter syndrome quite a lot. So you probably know what imposter syndrome is, but I didn't know what it was until later. But it means like when you're in a room of people, you always feel that you're not supposed to be there. You don't feel smart as everybody else. So I know I had it a lot when I was university. So actually my first year of uni, I wanted to quit. So I went to my academic advisor in university and I said, you know what, I can't do astrophysics. I need to quit. I'm not smart enough. And he was like, what are you talking about? Why you think that? And I was like, oh, everybody seems to understand things before I do. And then he was like, wait, give me a second. And he pulled up our rankings of all of our tests for the whole year to see where people sat in the class. And America's a bit different. There was 400 people in my classes and I was fourth in the class, right? And he was like, what are you doing? Why do you think you're dropping it? And I just think people always pretend to be something they're not, and they always make you feel a little bit insecure. And that's why it's just a nice area you said about Einstein, right? Like everyone knows he's the smartest man in the world, but he didn't grow up like this, like when he was 4 years old, right? Somebody said he couldn't speak. His parents were probably panicking. They're like, what's wrong with this boy? And Elon Musk, he actually quit his first university because he just didn't like it. He didn't enjoy it. But look at him now. He's like one of the most successful people. So I just think little things like that, like kind of gives you a little bit of hope to realize like you're actually doing really good and not to compare yourself to people as much. So yeah, that's my inspirational chat over. Rishid, perfect. Yes, thank you. That's a nice way to say it. And yeah, parabola, good job. So if I was to throw a ball up, when we throw the ball up, the speed is really high at the start, right? So since I let go of it, the speed's really high. But as the ball gets further and further up, we know it's going to slow down, right? It starts to slow down. And then here, it's completely stopped. So the displacement it has to be some type of graph that has a really high gradient at the start, because the speed's high, and then a low gradient. So either is option A, or it has to be option B. So if I look at these, this line is steep and then gets less steep. And this line's steep here, but it gets more steep. So the only one it could be is A. So it has to be this shape to show us it's getting less steep over time. Yeah, thank you, Gabriel A. And then when it's coming back down, it's going to get faster as it goes down. Speed increases. So if something's getting faster, it goes back down. Either it's going to be A or it's going to be B, right? Something that's getting faster. So what I do is I look at my gradient again and I can see A is getting more steep. So that makes sense, right? So here it has to be getting faster as it comes back down. And then I look to make sure. So it did say he catches it. So that makes sense. If it starts at zero displacement and I'm saying zero displacement is in his hand, and then he catches it again in his hand, its final displacement I can see in my graph is 0 meters because it ended up back in his hand, ended up exactly where it started. Okay, so fab. Okay, so we're going to practice one more. Okay, let's try the Feynman one. You didn't speak for 2 years at uni, at nursery. Sorry. My parents wanted to pull me out because they were worried. Yeah, right, Ari, like, and now look at you, like you're trying to do A-level physics. Like think, for even people know you're smart anyway for saying you do A-level physics. You're going to get so much respect when you're talking to anyone in other schools, like, oh, what did you pick for A-levels? I'm sure you've already had this. And you're like, oh, I picked physics. Everyone straight away is like, whoa, you must be so smart. So yeah, just, you guys are smarter than you know. A stationary point in the middle, because when you throw a ball up, if you look at it, it doesn't really look like it stops, because when it gets that highest point, it's like for a nanosecond, technically it stops. And that's why we say it's zero speed there. But because it turns around so quickly on your graph, you wouldn't plot it. But yeah, like technically there is like a stationary point there. Yeah, Garrick, actually, yeah, perfect example. So I think, did we introduce Garrick last time? So yeah, Garrick, I used to teach, and exactly what he said. He was the only one who asked questions. Everyone else just sitting there. And I was like, do you know that means you're the smartest? It doesn't mean you're not. Parabola but inverted. Oh, okay. So So let's draw a picture. So it says Feynman drops a ball from rest. So the ball is currently in his hand. And then it wants to go down to the ground. That's what it says. And it's going to bounce and come back up. Okay, so I have to think about what's happening. So again, I'm going to sketch my graph first. So time in seconds and displacement in meters. Okay, so I think if I drop a ball, I know it's stopped at the start. And as it falls, it's going to get faster. Okay, so as it falls, it gets faster. So again, I draw my curves and I have to figure out which curve it's going to be. So it's either going to be something that falls and gets faster. Oops, sorry. Or where am I struggling here? Sorry. Or falls and gets, so I basically have to figure out which one of these means it falls and gets faster, right? So I look at it and I can see here, that's it falling and getting faster because the gradient's getting more steep. So the first thing it does is it's going to have a gradient that's getting more steep. Okay. Is everyone okay that, again, remember we said that we're taking down with me always to be the negative direction. So that's why I didn't go into the positive region of my graph, because it didn't go up, it went down. So that's why we went into the negative region of our graph. Okay. So give me a plus if we're happy with the first thing I've drawn there. So the first thing we draw was, thank you, Angel. Yeah, so first thing we saw there is that it's gone, we've dropped it, so it's went down. So I went to the negative region of our graph, and we can clearly see the gradient here is getting more steep because it's getting faster. Fab. Okay, now, when the ball hits the ground and comes back up, it's going really fast at the start, and then it gets slow. So I have to figure out, it's going to be a curve again because it's accelerating, or decelerating in this case. I have to figure out, is it going to be a curve that looks like A, or is it going to be a curve that looks like B? Pop in the chat. Which one of those two looks like something that's decreasing in speed? A or B? Something that's decreasing in speed. So I got one person said B. What do y'all think? Is A or B something that's decreasing in speed? Got a few A's now. Oh, we're mixed half and half here. So again, remember, what you got to do is you look at A and look at the gradient in that line. Is that something that's gradient's increasing over time or decreasing? Look at B, is that gradient increasing over time or decreasing? Oh, we're still in debate. So again, remember, we're saying it's slowing down. So we want a gradient that's getting less steep. Yeah, thank you, Area, as well. Yeah, A's, Aaron, good job. Yeah, Brian changed his mind. Good job. Yeah, so clearly it has to be A, because if we look at it, if I look, the gradient here is really steep, and then that gradient's getting less steep over time. So A is something that is slowing down over time. Okay. And then it went back to his hand, which makes sense, is why I'm going to bring it back to displacement here of 0. Okay. Really quickly though, what do you think? Will it actually go back to his hand? Aishan, you just woke up. Okay, so will it actually go back? Will it actually go back to his hand? So like if we actually did it perfect, the question told us it goes back to his hand, which is why we drew it this way. Yeah, but it's not, right? Can anyone verbalize why? So technically it should look like this, right? It's never actually going to reach his hand again. It's going to be it's going to drop. It's going to get to some height slightly below his hand. You probably know that when you bounce a ball, right? You have to catch it at a lower height. Yeah, good job, Area, because of air resistance, right? So it's going to be, there's some of that energy is going to get lost. Not all of its initial gravitational potential energy is going to go into the kinetic energy, right? So we're going to lose some energy due to, yeah, exactly. We're going to lose some energy due to their surroundings, air resistance, and then also this impact point here. Okay, what actually happens is your perfect ball, when it hits the ground, it doesn't bounce the ground and stay exactly the same shape, right? You've probably all seen it. They get slightly deformed. So because they get slightly deformed, there's also some elastic potential energy loss there, okay? Because it's being deformed on impact, and then it comes back up again. There's quite a few points where we're losing energy, and then it's come back up again, like you all just said, there's more air resistance. So that's why technically it should never actually get back to his hand, but we drew it this way because that's what the question asks us to do. Yeah? Okay, well, I think that was quite intense for today. So we've got 3 minutes left. I think we'll move on to do our units, okay? So again, today and this whole summer school is just trying to get you ready for your first few months of year 12. So it says complete the units, okay? These you need to know. There's no way you can pass physics without knowing every single one of these, okay? So I would highly recommend you learn these as quick as possible, because your teacher is not going to spend a whole lesson teaching them to you. You'll be shown them and expected to learn them. But yeah, straight on it, Siri, thank you. Femtometers, and good on you, knew what femto was. Femto is times 10 to the negative 15. So it's called a femtometer. Femtometer. So use femtometers when you're talking about, you'll start to look at electrons and how they can diffract. So femtometer or femtometers, you look at nuclear size. So the size of a nucleus is a femtometer. So just write that out because Sierra was brilliant. It's called a femtometer. So super small, negative 15. Yeah, tera, nice. You knew what tera was as well. Good on you. So tera is super large. So this is a terameter, and it's the same thing. It's times 10 to the power 15 bigger. Terameter. Nanometer, thank you, CFK. So nanometer is times 10 to the negative 9. So your nanometer or nanojoule. Yeah, micrometer is what we call this one. Yeah, micrometer is what this one is. Yeah, giga, good job. Times 10 to the power 9 is a giga, super large. Times 10 to the power 9, or like a gigabyte, we know is big. Micrometer is times 10 to the negative 6. Thank you. The easy way to do it is 3, 6, 9, 12, 15. Right, they'll get smaller by 3s. So again, if we look at that pattern, 3, yeah, mega, thank you, is times 10 to the power 6. Okay, it's your megameters. Okay, so these, does anyone know what P stands for? Did anyone write it out? What does P stand for? So again, we know that's millimeter, we said. MILLI, millimeter, that's our kilometer, kilometer. That's our mega, like megabucks. Yeah, monkey, good job. It's picometer. It's a picometer. So times 10 to the power 12. So it's kind of like the size of an atom rather than the size of a nucleus. Times 10 to the power 12, you don't do. Actually, I'm not going to lie to you. I don't even know because I've never used it, ever. I don't know why. Now you made me think about it. I never even thought about that before. Okay, so today, remember, take a picture of this or write it in your work pack. These are super important. They come up all the time. So the same way, in your GCSE physics, they'd ask you like a question like you've got 10 milliamps and you had to remember, oh, I can't do anything until I convert that into amps. All the time now you'll be given, like say you're doing electrons, you'll be given that you're given 10 mega electron volts. You'll learn about this later. Or 10 megajoules. Or you're looking at a nucleus and you'll be told it's 10 femtometers in size. You need to remember those. Okay. And it's not like GCSE. It's not that you get a mark just because you remember to convert it. They're assuming that you know how to do this or you can't get the right answer, right? Yeah, so that's us done today. Lesson 2 done. And there is another homework there for you if you want to have a go at it. So you can just get in hand of how a course would be. So hopefully you're finding it useful. And thank you again for being like really active in the chat. And you can give us feedback on Trustpilot as well. Like if you have anything you want to like see better, anything you like better, and let people know about it as well. Yeah, Rashid, enjoy chemistry. I hope it's good. I'm sure it's LaJoy, isn't it? 100% it's LaJoy. You're so welcome. Good job, guys. Ari, you want to go to Queensmary? Aishan, yeah, we just woke up, man. Yeah, Angel. I think the next topic we're doing is we're going on to more graphs. So we're doing Fiji graphs. So we're staying with graphs for a while, but at the end of each lesson, I'll try to finish a little bit early and then start quizzing you on them every time. So then hopefully by the end of the next, we've got 3 more weeks of lessons. By the end of the 3 weeks, hopefully you'll know them by then. So just at the end, I'll leave you like 2 minutes to quiz you on a random one. We got math today as well. Bye, guys. Bye, Chloe. Bye, Aria. Oh, yeah, you're right, CFK. I don't think chemistry starts to the 12th, isn't it? Yeah, thank you, Garrick. That was nice, Aria. Can you teach physics for MIT students? Should I know what MIT is? Like MIT. You want to go to MIT in America? Is that what you mean? David, I haven't seen you in the chat at all. Where have you come from? No, Rashid. Well, it's nice that someone remembered you there. I forgot about it, but yeah, I think chemistry is next week. Ari, you want to be in America? I'm gonna say university there is amazing. Hamza, Have you been here the whole time, or are you just coming in there the last 3 minutes? You just wake up like Aishan? David, you're just trying to get across to us here the last few minutes that you know what picometer is, eh? Hamza just came. Did you forget the time? Mine, it's 11 to 12. Adinif, I'm not sure I've seen your name either. Have I? Oh, I have, sorry. Adinif, I told a lie. Sorry, you've been active. I apologize. Yeah, bye guys. Right, have a lovely day. Hopefully you do have, I think you do have math, right? If you want to do it. And then hopefully I'll see you next Tuesday, right? So Tuesday, next Tuesday. You're watching Suits to 4 a.m. You're killing your brain, man. Picometers is like the size of an atom. So a picometer is like the size of an atom, where femtometer is more like the size of a nucleus. Timothy, are you doing year 13 as well? Or you mean you are year 13 and you just saw there the time, you're like, oh crap. Ah, right, Timothy, you're coming in for year 13. Yes, Timothy, you're good. We're not starting that one to 2. Right. As David says, adios.